What are you looking for?
Can I get the January?
Oh, the form? The sheet that I just handed out? Okay. I would just like to talk about something. What?
Where's type 3?
What?
Type 3.
Type
The
3?
night before.
Oh, yeah.
That's what I'm doing.
Okay. What?
10 hours equals 1 minute.
Yeah. So the problem that we're slowly, steadily creeping up to. You okay, Jonas? Okay. All right. What? Okay. Is shut your trap. We've got 1 week. 1 week before the break starts, and then when we come back, we have 12 school days after the break. Yeah, 12 school days. So here's the deal: is that we're planning on having our organic unit exam the Friday that we come back from the break, and then we're going to have 7 days of review. Now, the reason why we're having our organic unit exam on the Friday we come back from the break is because the Monday, then the next Monday, I don't know what the hell day that is, that's the 13th apparently, that's when diploma exams start, like the Part A's and things like that. So that, I'm pretty sure, and don't quote me on this, but I'm pretty sure the 13th is the English Part A, and then I think the 14th is the social Part A, and then I think the 15th is the FLA Part A, just for anybody, if anybody's FLA in here. So, and then we got 16th, 17th, there's nothing going on other than review those days. 20th, 21st, nothing going on other than review. The 21st is the last day of classes, and then we jump into math, English, social, biology, chemistry, physics, science 30, that kind of thing. So our diploma exam is going to be on the 28th at 9 o'clock in the morning in the BAM gym. I'll give you a sheet that tells you when and where it is and everything like that. But here's the problem: is that there's kind of 2 types of study habits.
There's actually 3.
Yeah.
There's actually 4.
There's 2 types of possibly successful study habits. Okay.
Possibly.
The first type, which I feel like is the most successful for the most amount of people. This is going to fit the bill for the vast majority of the individuals inside of our class right now. The slow burn method is if you have ever struggled in Chem 30 in kind of a couple different places, then this is probably the way that you want to study. So you don't have to do anything until kind of the last week of the holidays. But in that last week, what I would suggest is you spend 3 to 6 hours reviewing. It doesn't really matter that it's equilibrium, but spend 3 to 6 hours reviewing one of the units, right? So all of these units are totally interchangeable. If you wanted to do it studying organic chemistry, that's fine, because we're going to have an organic chemistry unit exam the Friday we come back. Whatever, it's all good. And then the next week, spend 3 to 6 hours reviewing the next unit. And then the next week, 3 to 6 hours reviewing that. And then the next week, which is the last week before our diploma exam, spend 3 to 6 hours reviewing that. So there's 4 units, and you should spend a little bit of time studying each of these units. This is a diploma exam. It's supposed to cover a lot of curriculum, right? The total study time that for this method somewhere in between 15 to 30 hours. Now I know that that looks like a lot. Like that looks like a huge amount of work. But this is really just, I mean, if you study for 15 hours, remember this is spread out over the course of a month. Like literally an entire month. This is 15 hours spread out. So you could do 25 minutes a day. And that would blow past that 15 hours easily, right? So it's not a ton of time. And if your priority is to do really good on the diploma exam, if that's a priority in your life, then you're going to have to give up something that's a lower priority. Do you know what I mean? You're just for a month or for a few weeks, you're going to have to give up gaming as much as possible. Or you're going to have to give up YouTube as much as possible. Or, you know,
Some watching.
Ugh.
Yeah, watching your videos.
Well, if you're watching my videos, then fine, whatever. Okay. I will try to be as available as possible when we're doing this. So, I don't know, we'll see how it goes. The second type, which is significantly less successful for individuals who never really got the information the first time around. Cramming, don't get me wrong, cramming is a perfectly acceptable style of studying, but only if you're the kind of person who you just need a refresher, you just need a review. If you're the kind of person who, oh man, if I'm being honest with myself, I really didn't understand this the first go around, then cramming's not going to help you. Cramming's not going to help you to learn, it's going to help you to review. Does that make sense? Okay. So if you're the cram style, then that means, you know, in the week leading up to it, you should spend 15 to 30 hours in the week leading up to the exam. That's what I would consider to be cramming. The third style, which has never helped anybody, by the way, this is the worst thing you could possibly do. Wait until the day before and try and study for 12 to 15 hours and realize you're boned. You're just absolutely screwed. So, I mean, there's that. Whatever. It's all good. No, please don't try. Diploma prep. Does anybody know what I mean by diploma prep? Rock the diploma. Yeah, rock the diploma, yeah. So, rock the diploma is great because there's going to be an individual who's literally going to teach you everything you need to know, right? But it's going to be really quick, really fast-paced because they're going to go through basically all of the information from the entire course in 3 days, right? 2.5 days, kind of. It counts as half study time because you're not actually putting in all of the work when you're doing diploma review, right? Like diploma prep is what I mean, rock the diploma. You're kind of sitting there passively accepting a lot of information. And so that's to me, that you should count that for half the amount of time. If you're studying at home and you have your cell phone beside you and you are actively going back and forth between your diploma questions and your cell phone, I would totally, every 1 minute, 10 hours is like 1 minute for that. It's just so, every time you look at your phone, you're interrupting the neurological connections that are trying to be formed in your brain. They're trying so hard to be formed, and every time you look at your phone, you completely interrupt that process, and you lose all the work that you've gained in the last 5 or 10 minutes. Okay? So please, please, please take this comment to heart. When you're studying, the worst thing you can do is have your cell phone open and beside you. The worst thing you can do is have social media accounts up on your computer and open and things like that. That's just the absolute worst thing you can do. Studying with friends is fantastic, right? Talking about it, discussing questions, trying to figure out different solutions, that's great, that's awesome, that's really powerful for people. But having your cell phone open and texting other individuals is not helpful. Does this make sense? Are we kind of okay with this? Yeah, so you have to make that choice for yourself whether or not you want to be the first style, the second style, or God forbid the third style. You know, whatever. You're, yeah.
Some people like it feels like they're super smart. Like Roger's not like the some person who can study at all. They walk through the door and they learn 100%.
I've never heard of that happening.
Walton, we'll see you on the 16th.
Mr. Zakowski and Mr. Zielinski have told me many, many times, because this is only my second time teaching Chem 30, right? So they've told me several times that if you study for less than 10 hours for this diploma exam, odds are your mark will drop by greater than 10%. That's just what they've worked out for themselves, is that because they always put a survey on the desk of the people who are writing the diploma exam, and they ask people to fill it out honestly, like how much time did you actually spend studying, what types of studying did you do, and they've done a little bit of analysis, and they have supported the conclusion that if you work for or study for less than 10 hours, then your mark will drop considerably. If you study for greater than 10 hours, then there's a chance that you will meet your unit exam average, not necessarily your class average, right? Does it make sense that if you're sitting at like a 70 right now, odds are your unit exam mark is somewhere in the 60s, right? Because usually that's the category people do the worst on, because it's the most difficult. So the diploma exam, a good indicator of how you'll do on the diploma exam is after studying for 10 to 15 hours, what's your unit exam average? That's probably what you're going to get on the diploma. So anyways, I don't want to bug you about it anymore. Yeah. Does anybody actually want me to print off paper copies of those huge ass review booklets from the classroom? Okay, so I'm just going to take a tally and I'm going to leave this up on the board so I know how much to print off. Okay, so hands up if you want me to print off copies of all of the review booklets. I guess pretty much everything.
Damn it, is it just like the review booklets?
No, the huge 60, 70 page review booklets.
Are you going to be here for like all of the exams? Or are you going to be here?
Yeah, basically, I'm going to be here during pretty much the entire time. There's a little bit of time where I'm going to have to, because the provincial government really kind of slammed our budget, and we were going to buy new conductivity testers, but instead of doing that, now we have to make our own conductivity testers in order to save a couple $100. So that's going to take at least a day for me to make conductivity testers. So there's going to be some time where I'm unavailable, but yeah, whatever, I'll be here for the most part. Cool. Okay, get out your notes. We did this on Friday, 9.4 aromatic compounds. Here, I'll take this one. What?
Apart from that we have after like the review.
Yeah, well, if you want me to. I mean, I'm sure between me and Mr. Zakowski, we can set up review sessions for...
Like what's the, like that week before, like the exam, like happen, like the last
We're reviewing. Yep. I'm going to be giving you special problems, or I'm going to be giving you time to work on something, like if there were things that you needed to work on that you didn't hand in or the semester, then you can bring it up, that kind of stuff. Yeah, I get it, Shelby. We have 7 days, right? We have 7 days-ish of review, so we got to do something. Okay, if you look on our calendar, I didn't put it, did I? If you look on our calendar, I said that tomorrow, right? This is the deal we made in class. Tomorrow we were going to have a quiz. So we're going to have our 9.1 all the way to 9.3 quiz. Aromatic compounds are not on the quiz, right? So this is, what is an organic compound? how to name and draw alkanes, how to name and draw alkenes, how to name and draw alkynes, and then isomers. That's like the 5 things that are on there. You're not going to get anything other than that. I don't know, it's 5 questions, something like that. I'm going to give you 25 minutes to do it. What? Okay, that's not 5 points. I don't know, it's 7 or 8 points. Okay, well, tough luck. We were talking about benzene, and benzene is interesting because it's extremely stable. Compared to other 6 carbon compounds, benzene is extremely stable. It's also really super carcinogenic and toxic, but you know, that's okay. We talked about naming our benzene rings, and it's the exact same thing as cycloalkanes and cycloalkenes and cycloalkynes, except what are we always going to end this name with? Benzene, right? So 1,2-dimethylbenzene, sure, whatever. 1,3-dimethylbenzene, sure, whatever. That's totally fine. Then we drew some. Then we talked about some diploma questions. We are going on to 9.5, crude oil refining. You doing okay?
No.
No? You need to grab a new notes packet?
I think so, yeah.
Okay. They should be in the bin. 9.3.
I don't know where I put
Oh, well, you skipped a lot of stuff. Many of our organic compounds come from the refining of crude oil. Hey, where do we get crude oil from?
The ground.
The ground, either under the sea, or we get it from under where places used to be seas, like in Alberta, right? Alberta used to be covered by a big sea, and that's why we have rich oil deposits. Crude oil is a mixture of several thousands of different compounds. And so when you extract crude oil, you need to be able to separate them into a bunch of different compounds. Now there's several different ways that we can do that. Typically we talk about separating them based on boiling point or solubility. Now I want to bring your attention to the idea that crude oil could be a mixture of very different compounds. Crude oil is a mixture of bitumen. Does anybody know what bitumen is? We'll talk about it. It's a mixture of bitumen, liquefied natural gas, LNG, liquefied natural gas. Another name for liquefied natural gas is like propane and butane, ethane, things like that. LNG stands for liquefied natural gas. Nope. We're going to look at what the hell bitumen is.
Okay.
Good? Good? Okay, bitumen. I'm trying to think how I can describe bitumen. Bitumen is, it's kind of like a solid, but it's not. It's not really a solid. It's actually a liquid. It's just an extremely, extremely, extremely viscous liquid. Does anybody know what viscous means? Thick. Unpourable, right? So, yeah, think molasses, right? So water pours very easily. Does honey or molasses pour very easily? No, and bitumen is even more so than that. If you were to leave bitumen, just a chunk of bitumen out for, let's say, 10 years, it would start to flow. Gravity would pull it down and it would start to spread out and flow. But it's not very viscous, or sorry, it's extremely viscous, which means it has a hard time flowing. What we can do is we can separate all of these compounds, because let's take a look at a couple of these. Liquefied natural gas is basically things like propane and butane. So what's the formula for propane? Good. C3H8. And we're going to take, instead of talking about bitumen, the kind of the largest organic compound we really like to talk about is paraffin wax. And I don't know how to spell paraffin wax, but that's how I'm going to spell it. Oh, that's worse. Oh man, that's way worse. Uh-oh. Blah. Okay, so liquefied natural gas is propane, paraffin wax. Does anybody know the formula for paraffin wax?
That's the one that has like whatever 7.62.
It's got trillions of different isomers, right? Yeah, that's the one.
I remember Googling that. That was so fun.
So let's take a look at this, and let's try and see, well, which one of these is bigger? Paraffin wax is bigger, right? Which one of these is going to take more energy to boil? Paraffin wax. Does that make sense? Because it's a larger molecule, it's got more electrons, and when you have more electrons, there's a greater London dispersion force in between the different molecules. Do you remember that?
Nope.
No?
Barely.
What?
I feel like that unit is very quick.
Oh man, yeah, I probably just prodded a part of your brain that hasn't been active for some of you, probably a year and a half, but that's totally fine. That's okay. Does anybody not remember what the hell London dispersion is?
It's a bonding.
You never learned about London dispersion forces? London forces?
Yeah.
In Chemistry 20?
That was bond. It was part of the bonding.
Yeah, it was part of the bonding unit, for sure. Yeah.
That unit.
Oh man. Okay, I just want to double check. Perfect. Okay. No. We're gonna go over it. We're gonna go over it here in a little bit. So, I just want to show you how the separation works. At the very top of your slide here, let's put.
I think I did this exact same thing in grade 8.
Yeah, you could have. Yeah. Fractional distillation is when you distill something. Now, distilling something, it just means you're going to heat it up so that it boils, and then somewhere else you cool it down so that it condenses. That's all distillation is. So if I was to distill water, have you ever heard of distilling water? Yes. No? Yes? Kind of? Sort of?
Yes.
What? Pardon? That's what distilled water is. Yeah, sorry. Hopefully that's not like a big shock to you or anything.
Whoa.
This is the worst marker in the world.
Beautiful.
Yeah, uh-oh.
Does it?
Actually, distilled water has like.
Okay, so Here, that's a terrible marker, sorry. Here is, nice. Here's an Erlenmeyer flask that it's got some water in it, but it's a special kind of water. Let's call it salt water. So what is salt water? Ocean. It's oceanic water, right? Good. Okay. So what's going to happen is we've got this salt water, which is a mixture of salt and water, and we've got a stopper in our Erlenmeyer flask, but we've got a hole in it, and inside the hole, we've got a tube, and that tube can go and it can flow through something that's cold, something that's colder than it. So if you had this tube running through something that was just cold air or cold water or something like that, then you could, so we're going to heat up the water. What's going to happen to the water? It's going to vaporize, right? So in here we've got a mixture of H2O and salt. Which one of these two vaporizes more easily? The H2O. So the H2O vaporizes, it rises up through the tube, and then as it goes through the tube, it starts to condense. What is the process of condensing?
Condensation.
From a gas to a liquid. Thank you. The process of condensing is condensation. Perfect. So we've turned from a gas to a liquid, and what's going to happen to the liquid? It's going to start to pour out. And what have we successfully done to this mixture? Yeah. Oh my God, we distilled it. Yeah, thanks. We've separated the mixture between the water and the salt. The salt cannot boil at the same temperature as the water. So the water leaves, and what remains inside the flask? Salt. The salt. So we've successfully separated the mixture. And so what we can do the exact same thing here in this tower. We're going to take crude oil. Remember, crude oil is just a mixture of thousands of different compounds, organic compounds. And what we're going to do is we heat up that crude oil so that the vast majority of it vaporizes. So we evaporate as much of the crude oil as possible. Now, if something turns into a gas, a really, really hot gas, what's going to happen to that hot gas when it goes into the tower? It's going to rise. And anything that doesn't vaporize, like the bitumen that we talked about earlier, the bitumen is going to fall. And so the asphalt, that's one of the things we use bitumen for. We use bitumen and asphalt for making roads. We get paraffin wax out of this because it will boil less easily than a lot of other things. Okay, so we're going to put in our mixture, which is crude oil. I know it says it right there, but that's our mixture. And we're going to heat it up. Question?
So, different stages and different levels of warming up crude oil will produce things like asphalt. Like, if I heat it up to a certain degree, I'll get asphalt, and then if I heat it up...
Nope. If you heat it up, you will separate the substances that were in there normally. So in here we've got water and salt. The water separates from the salt. Just like if I heat up crude oil is not just made out of bitumen. Crude oil is a mixture of thousands of different chemicals. Some of them are easier to boil than others. That's all that is. So go ahead.
I only understand this diagram because it's saying from crude oil you can get asphalt wax, lubricating oil, fuel oil, diesel oil.
All of these things are in the mixture. They're all in the mixture.
Okay, and if you warm it up to a certain degree, you get different things? Is that what it's...
Let's talk about it.
Okay.
Because we're not done the diagram.
Okay.
Okay. What I want you to think about. Let's take a look at this tower. What part of the tower are we heating up? The bottom. So what's happening in this tower is that the bottom is really hot and the top is colder than the bottom, right? So let's put in some fictitious temperatures, if that's okay with you. So way down at the bottom, let's call this 500 degrees Celsius. And way up at the top, let's say it cools all the way down so that it's like room temperature at the top. So let's say it's 200, or sorry, not 200. 200. Let's say it's 20 degrees Celsius. Let's think of two different compounds. Let's think of two different compounds. In our mixture, we're just going to think of butane. For the purposes of this, we're just going to talk about butane, and then we're going to talk about, let's talk about decane, okay? Butane and decane. Now, somebody with a phone that's actually going to use it for educational purposes, can somebody look up the boiling point of butane and somebody else look up the boiling point of decane? So the boiling point of decane is 174.1 degrees.
And the butane is -1 degree Celsius.
Is -1 degrees Celsius. Good. Perfect. So let's follow these two different compounds as they travel through the fractional distillation tower. Now remember, what temperature does water boil at? What temperature does water start to boil at? 100 degrees Celsius. So if the temperature of this room was 80 degrees Celsius, could the water boil? No. So what state of matter would the majority of the water be in? Liquid. If this room was 120 degrees Celsius, could the water boil? Yes. So what state of matter would most of the water be in? Gas. It would be a gas. So as you go through this tower, if the temperature is hotter than this, what state of matter will these chemicals be? A gas. Does that make sense? If the temperature of the tower is hotter than this, then it will be a gas. If the temperature drops below these temperatures, what's going to happen? They will condense. And so let's follow these as they go through the fractional distillation tower. Crude oil is more than just butane and decane mixed together. Okay? Please, please, please understand it's more than just butane and decane mixed together. But for the purposes of this, we're simplifying, we're just going to talk about two chemicals. So as this mixture goes through, it goes into here, and what do you think? It's 500 degrees at the point where it goes in. So what's going to happen to both of these chemicals? They're both going to boil, okay? And so let's do a nice old gradient here. So if this is 500, this will be 400, this will be 300, this will be 200, and that'll be 20. I know that it's, yeah, whatever. Okay, as this mixture goes through, they both, would you agree, they both boil? So they go through here and into the next level. Now, this next level, what temperature is this chamber in? It's 400. So do either one of these things condense? No. So they continue to go through. And do you know why I'm drawing this? Because it has to go through like that. It has, the way these towers are set up, things can't fall back to the previous level. let's say something condensed here. It would condense and it would pool, but can it go back down to the next level? No. If it overflows, yeah, but all you need is you just need a pipe taking the excess material out. Does that make sense? So, okay, either of these, are they going to condense yet? No, so we keep going. Either of these, are they going to condense yet? It's close, but no, it's not. Neither of these are going to condense yet. So then we finally get back up, we get up to our top layer here. Are either of these going to condense yet? Yes. Which one? The decane. The decane is going to condense. Does that make sense? So what we're doing is we're distilling these off in fractions. There's a fraction up here where the decane is going to turn into a liquid and it just flows out through a pipe. Okay? Now, does the butane ever condense? If it ever got colder than 20 degrees Celsius, right? So what's going to happen is it gets pumped out through the top, and then we can condense it in a tank somewhere else. So we're taking these off in sections or in fractions. It's called a fractional distillation tower because each fraction of the tower is condensing a different temperature of these compounds. Yeah, Denver.
Are those percentages on the side like the percentage of the crude oil that turns into that?
Yes.
Okay.
Yeah. So this is in general approximately 40% of the crude oil that we use goes towards gasoline. Approximately 7% of it goes towards jet fuel and kerosene. Now I want you to understand that jet fuel and kerosene are basically the same thing. Okay? They're just really, really high energy rich organic molecules. Then diesel oil, then fuel for like really, really large fossil fuel burning engines. Lubricating oils, things that are really, really thick, you're not going to burn them. And then paraffin waxes and asphalts and stuff like that. Now the bitumen has a boiling point of about 800 degrees. So does the bitumen ever boil? No. So what happens is it spills out and it goes down into the bottom layer. Does that make sense? So we're taking them off in fractions. Sanjana, did the process of following two chemicals as they went up the tower actually help us?
Yeah.
Okay, good. Awesome. Now, let's talk about why those two chemicals have different boiling points, because this is really important and it goes back to chemistry 20. The boiling point of a molecule depends on certain factors in decreasing importance. And this is because this is going to talk about all the different intermolecular forces. Do you remember the different intermolecular forces?
London forces.
There were London forces, sometimes called London dispersion forces. Okay.
Hydrogen.
You would have just said that.
Oh, hydrogen.
H bonding.
It was like the
There's like
These are all types of intermolecular. Inter means between two different molecules. So metallic bonding is a type of intramolecular bonding because it's between atoms of the same substance. Yeah. Yes. Dipole, right?
your product.
Now, do you remember which one of these was the strongest? Pound for pound, the one thing that made the biggest difference. So what that means is if you had two chemicals that were approximately equal weights or approximately the same number of electrons, it was hydrogen bonding that made the biggest difference. But if you had two chemicals that were vastly different sizes, vastly different masses, or vastly different amounts of electrons, then actually it was London forces that made the biggest difference. But in terms of comparing different chemicals, hydrogen bonding is going to be our most important factor. Okay? If two chemicals are approximately the same size and one has the ability to hydrogen bond, it will be harder to rip away from its friends. Does that kind of make sense? We'll go through it in a little bit here. Okay. So this is the most important thing that you need to look for, the presence of hydrogen bonds. Now, what are hydrogen bonds? How do hydrogen bonds form? Do you remember?
They use a special fluorine or chloride.
It's either the presence of an oxygen-hydrogen bond,
Fluorine hydrogen.
a fluorine-hydrogen bond, which there's only one substance in the world that has fluorine-hydrogen bonds, and it's hydrogen fluoride, so whatever. Okay? And then nitrogen-hydrogen bonds.
I do not remember.
Do you? I'm curious. Do you remember this from Chem 20? Yeah. No. And you don't need to know this for the diploma exam, but the reason why this is that hydrogen is so small. Remember, it only has one valence shell. So I'm going to draw this. I don't want you to draw this. So put your pencil down. Just don't worry about it. What does a hydrogen atom look like? How many protons are in a hydrogen atom? One. And how many electrons are in a hydrogen atom? One, right? And so if you've got a hydrogen atom, what that means is that you've got one electron and one proton, and in a bond, when hydrogen is attached to something super, super, super duper electronegative, like oxygen, fluorine, or nitrogen, that thing that's electronegative can start to steal the electron away from the nucleus. Now, if you steal the electron away from the nucleus, this basically becomes a bare positive charge all by itself. And that positive charge is extremely attracted to what things?
Hydrogen.
Nope. Negative charges. And things that have negative charges are often electronegative. And so that's the reason why it's okay if you didn't understand that. It's okay if that was like too quick of a description for why this is, and that's totally fine. All you need to know is if a chemical has hydrogen-oxygen, hydrogen-fluorine, or hydrogen-nitrogen bonds, then it will have a high boiling point. The next thing you need to look for is the size of the molecule. What's going to have a higher boiling point, a big molecule or a small molecule? A big molecule, and that's because a greater number of electrons equals a greater London force. The more electrons something has, the greater attraction it has to its neighbor. And then the last thing is the amount of branches on the molecule. Now, I'm going to put an asterisk through that or beside it. That I've never seen that tested directly on the diploma exam, but it is technically part of your curriculum, so I'm going to teach you about it. And the reason why that is what do you think is going to be more attracted to something else? Do you think objects that are really close together, do you think they're going to be more attracted, or do you think objects that are really far apart are going to be more attracted? Really close together. Does that make sense? Because it's closer and the forces are going to be stronger. Any electrical forces between them are going to be stronger. Now, I'm going to draw two molecules, and they're going to be the same approximate size, and I want you to let me know if it can get closer to its partner or if it cannot get as close to its partner, okay? So I'm going to draw this molecule and its partner, right? Two of the same chemical. And then I'm going to draw this molecule and its partner. And they're approximately equal sizes. This is approximately the same size as that. Now, which objects do you think can, on average, get closer to each other? Do you think the two rectangles can get closer to each other? Or do you think the two circles can get closer to each other on average? When I take a look at this, that's how much surface area contact is there between these two things? There's a teeny tiny little bit of surface area contact. When I take this and push them together, how much surface area contact is there? There's lots. So there's lots of attraction here, but there's only a tiny amount of traction here. Does that make sense? So which of these two things is going to be harder to rip apart from each other? The rectangles. Okay? All right. Okay, so let's take a look at this. I've got 4 molecules here. Which of these molecules is going to have the highest boiling point? And what I mean by that is if I had a beaker of this chemical, so what that means is trillions of these molecules all together, and I had a beaker of this chemical, trillions of them all together, these were all in separate containers, which ones would be the hardest to separate from their friends? Which chemical in here has the strongest attraction to its partners, to its own family members? That's weird. I shouldn't have said that before. Jordan. Why the top left?
Because it's got an oxygen hydrogen.
So this is hydrogen bonding, right? So it's gonna have the highest boiling point. Yeah.
Does the polarity also make it high?
Yeah, it's not only is it hydrogen bonding, but it's also a polar molecule. Yeah, I agree with you. And so both of these things contribute, but the fact that it has hydrogen bonding is, yeah, it trumps everything else. Yeah. Okay, so now that we're done with that molecule, look at the other 3 molecules. Which one of these molecules is going to have the next highest boiling point?
Number 3.
Do you think it's the one on the bottom left or the one on the bottom right?
Bottom left.
Bottom left?
Bottom left.
Bottom right?
Bottom
Bottom
left.
left?
That one.
Bottom right? Okay, what's the formula? What's the formula for top right? C3H8. What's the formula for bottom left? C5H12, right? There's 5 carbons, and I don't see any double bonds and I don't see any rings, so it's 2n plus 2 hydrogens, right? And then what about this one? C5H12. Okay, so out of these 3, which one is going to be the easiest to separate from its friends? Top right. This is going to have the lowest boiling point. Do we agree with that? Yeah, it's going to have the lowest boiling point. So now it's between this one and this one. Are they the exact same size? Yeah. In general, they have the same mass. They have the same molar mass, right? Okay. So what that means is now we're stuck, and we have to choose between which one of these has the strongest attraction to its partners. Which one has the strongest attraction to identical versions of itself? Jordy?
Isn't the bottom left one polar?
The bottom left one is not polar. In a sense, it's asymmetrical. Would you agree?
Yeah.
Which kind of makes it polar.
But it did make it polar.
No.
After my 2.
Okay, now I want to be super clear about this, Jordy. These are all carbon-hydrogen bonds. Every single direction you see is the exterior of this molecule is carbon-hydrogen bonds, right? So yes, while I totally agree that this compound does have some bond dipoles, but the fact that they're all surrounded by the same bond dipole in a bunch of different directions, they all cancel out, right? Same one here. Okay, so which one of these, what's next? Yeah, it's not, that didn't work very well. That didn't work
Amount of branches.
Yeah, so hydrogen bonds out, size of the molecule, we can't use that to discriminate between them, right? So it's just the amount of branches. Which one is more branched? The one on the left. Does that mean this has, can this get closer to its friends, or is it being pushed further away? This is being pushed further away. So this is going to have a lower boiling point. It's going to be easier to tear it away from its friends. So that means the next highest is going to be this one, number 2, and the next, and then that one. Okay? Does that kind of make sense? Okay, so which one of these, if you were to do fractional distillation, if you were to perform fractional distillation, which one of these would come out at the very top of the tower?
Number 4.
The C.
Number 4.
He's getting ready to.
The top is colder, and that means it's the easiest to boil, right?
So 4.
So number four comes out at the top. Which one comes out at the bottom? Number 1. So that one's the lowest, right? And then this one's the next lowest, and then that one's the next lowest, and then that one's the next lowest. Good. So now you know why paraffin, wax, and butane come out at different points, because they have different intermolecular forces. Is that kind of okay?
Yeah.
All right.
I thought he was going to be a classic feature.
Okay.
Use this, but now you're all. That's a classic feature.
No, no.
Turns out I taught you.
Something that you're going to have to be able to do, this is in your program of studies, and it's in your review booklet as well as one of the outcomes that you have to know, is you have to be able to look at a homologous series.
Whoa, that's a word.
Does anybody know what the prefix is in homologous? Homo, what does homo mean? Same. Homo means same, right? Okay. Oh my god. Okay. Homologous series. A homologous series is a series of compounds that they're mostly the same, but they're changing by one tiny little aspect every single time. Let's take a look at this homologous series. This is a homologous series. Tell me what's changing in this homologous series.
You're getting more carbon.
We're adding an extra carbon every time. And 2 hydrogens, right? Is that okay? We're adding an extra carbon and technically 2 hydrogens every single time. But that's what the homologous series is. The homologous series is 1 carbon, 2 carbons, 3 carbons, 4 carbons. So all you have to do is tell me what's the next substance in this homologous series. Pentane. Does that make sense? All right. Okay. Let's take a look at this next homologous series and tell me what's changing in this homologous series.
The amount of hydrogen.
Yeah, it's the amount of OH groups, but that will affect what, Maj?
Hydrogen bonds.
The amount of hydrogen bonds, right? So what we can say in this homologous series, or in these homologous series, we can say that which one of these is going to have the lowest boiling points? Is methane, ethane, propane, or butane? Which one's going to have the lowest boiling point? So this is the lowest boiling point, and this is going to be the highest boiling point. Which one of these is going to have the highest boiling point? probably not going to be the middle one. Can you assume, right?
Yeah.
Just by process of elimination, it's either the one extreme or the other. Which one of these is going to have the highest boiling point? Which one is going to take the most energy to rip apart from itself?
The right one.
The one on the right. Why is this one going to be the hardest to rip apart from its friends?
Because it has 3 hydrogens.
It's got 3 different places that it can hydrogen bond at, right? This is the highest boiling point, and this is going to be the lowest boiling point. Does that make sense as far as the homologous series goes? All right. Perfect. So, I would like you to take a look at these 2. The one thing I forgot to say, the one thing I did forget to say, sorry, is this fractional distillation is separating things by boiling points. A boiling point is a physical property. When you boil water, do you turn water into some different compound? No. When you boil water, yeah, you're just changing the state of matter, right? It's a liquid here, it turns into a gas, turns back into a liquid. That's a physical property of every substance, but the specific temperature is dependent on that chemical, right? So these are all, this is just separating things based on physical properties, that's all it is. So you got 2 diploma exam questions, I would like you to answer them. Yes, yes.
Oh, whoops. It is.
Smarty pants. That's supposed to say talk. Nice looking.
You sure?
Legible.
What is your name? Okay.
No, they're not the same structure. This is like butane something all. This butane something else. You don't know what an all is, but the all is so they're the same but they're gonna have different structures, right?
I use a voice changer. Everyone was like,
Are we good? Do you need any more time to answer this? No? Okay. So question number 26. In a fractional distillation tower, hydrocarbons are separated based on physical property of what? Boiling point, right? You're not melting them, you're turning them from a liquid to gas, so it's boiling point. So that's out, that's out. compared to the number of carbon atoms in the molecules collected at the bottom, the number of carbon atoms in the molecules collected at the top of the tower is going to be greater or less. So, compounds collected at the top of the tower, are they tiny or big?
Tiny.
They're tiny. Does that make sense? So do they have less or more carbons? Less.
I hate wine.
Was that a particularly difficult question?
No.
If you didn't know what a fractional distillation tower was, how would you be able to figure it out?
No.
Probably not. Okay. Maybe, but you would have to know that the substances that are lighter usually boil more easily, and so they go to the top, right?
Yeah.
But yeah, that's fair. Okay, using only information contained in the table above. When the alcohols in the table are compared, they have the same what formula? Okay. Let's take a look at this. You don't know what the hell an all is, except you kind of do. Are there any chemicals you know of that end in all? Methanol, propanol, alcohol, right? Alcohol. These are all alcohols. Okay, what? What is the formula for ethanol? What is the formula for ethanol? You never had to memorize this?
Actually, no, maybe. I don't remember. I did, we though.
I don't remember that ever in my life.
Okay, do you, just give me 1 second, okay? But don't let me forget about you guys. The name of this compound is ethanol. Why is this called ethanol? Because it's got 2 carbons, right? Yeah? Does that make sense? It's got 2 carbons. And why is it called ethanol? Because it's got an OH group on it, right? So these all have OH groups on them. You could figure that with a little bit of deductive reasoning. You could figure that out. Go ahead and get off your phone now. Okay, let's think about this. If this is butane 1-all or butane 2-all, do you think they have the same structure? If something is obviously attached to the first carbon here, and that same thing is attached to a different carbon there, do they have the same structure? No, they can't have the same structural formula. They have to have the same molecular formula. Now, are they differing? Do you think they differ by chemical or physical property? Physical. They have different boiling points, and boiling point is a physical property. Good. Okay, don't let me forget about you guys. Yeah. What? Is fentanyl?
Yeah, fentanyl.
It's fentanyl. I'm pretty sure.
told you. You didn't know either. Why did you ask? Why are you doing
I'm getting it.
Go to Halls.
No. Let's just take a quick second and let's take a peek at fentanyl.
Whoa, so are we taking a trip?
No.
Chem Spider.
Yeah, Chem Spider. Hell yeah.
Is that a good website?
Yeah, it's an awesome website.
Well, that's a very big Chem Spider.
Okay, shh. This is maybe possibly important for your quiz tomorrow.
Okay, I'm ready.
Could you count the number of carbons on this structure?
Yeah.
Yeah, you should be able to count, right? Yeah, totally. Now, what I'm asking is this an aliphatic compound? Yes or no? Is this aliphatic?
No.
What it means.
That's tough. If you don't know what the word aliphatic means, do you know what the term aromatic means?
Oh, that's
What, Macy? Good. Aromatic means somewhere in here you have to contain a benzene ring. Is this an aromatic compound?
Yes.
Then it is not aliphatic. They are mutually exclusive. You cannot be both. So this substance is aromatic. It is not aliphatic. Good. And you could totally count how many carbons are in here, right?
Are aromatic and stuff like that on the quiz tomorrow?
The terms aromatic and aliphatic were introduced to you in 9.2. So yes, they could be on the quiz, but remember, naming aromatic compounds is not. Just the identification of whether or not something is aromatic or aliphatic. That's all. If you see this ring, what is it? Aromatic. If you see this ring, what is it? It's aromatic. If you don't see this ring,
Whoa.
aliphatic. Because there's no, right? Good. How many carbons are in here? Go ahead and count.
I did.
Okay.
I don't want to be wrong.
6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Okay. Yeah. I want to give you your major assignments. I don't have to give you your major assignment. If you would rather get it later, that would be fine with me. There's 5 minutes left, yes. What? Yeah. That's a Did people talk to me about it today? You've already been given an entire, literally an entire week, right? Okay, so Joe just asked me if today was the last day to review the unit exam that we wrote like a week and a half ago or whatever. And my answer to that was, yeah, I think somebody conned me into allowing today to be the last review session because we had literally an entire week last week to do it, and the deadline is like a week, right? But somehow somebody conned me because I have a weak heart and I'm a weak-willed individual. So somebody talked me into it. So I guess today's the last day to review the test, Alicia. I haven't marked the post. I was at a Kerlin Monsfield coaching. Oh, good question. This is due
Tomorrow.
Oh,
that'd be fun.
Bad idea.
13, 12, 11, 10. I think it's January 10th.
Okay.
Why are you counting that way? Oh, that way.
Why didn't you tell me you don't start with pinky?
No, I do not start with pinky.
Do you start with big toe?
It's due Thursday, January.
11.
Whatever the Thursday is. I don't know.
I'm checking. It's that's a Saturday, Walter.
Is that a set?
So the 10th. 10th is a Friday. Look, it's the same one you used.
Thursday, January 9th, I guess.
Wait, I have those now.
Because your exam's going to be Friday, January 10th, right?
So then for the reading test, this week?
Yeah, this week. Yes. 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 You are not allowed. Let me be very clear. You are. I don't think anybody signed up for any rewrites. What? On the door? Whoa. Oh, sorry. There's a sign-up sheet and it's been there for a week to be able to rewrite. So yes or no, have I told you that we're doing rewrites last week and this week? And not after Christmas? Okay, so we've got 4 days left for rewrites and nobody's asked me to do a single rewrite.
Imagine having a legendary class in this.
I get that you're smart.
Sure, hustle. What do you call it? Go right now.
I mean,